we will start the discussion on matrices, matrix operations and determinants. So, let us get to matrices. So, what are matrices? So, visually we think of matrices as an arrangement of scalars. So, what we think of is that if you want a matrix, we represent it as some arrangement of scalars. So, for example, you could have a matrix like 1 3 4 1 2 2 1 3 0 2 minus 1 7. So, this is an arrangement of scalars and this is referred to as a matrix. So, we can say that matrix is an arrangement of scalars into rows and columns. So, a matrix has to be in general a rectangular object. Okay. So, you can also have what are called as square matrices. So, a square matrix implies number of rows equal to number of columns. So, now the notation we will use for a matrix. So, notation for matrices, okay, if A denotes a matrix, A is a matrix, okay, it is denoted by an rectangular array, okay, and I'll just start with it in general and then I'll just explain to you what we are talking about. So, the elements of A are denoted as A little a 1 1, A 1 2, A 1 3 up to A 1 n. The second row you start with A 2 1, A 2 2, A 2 3 up to A 2 m, and you go all the way to the A n 1, A n 2, A n 3 all the way up to A n m. Okay. So, this matrix has n rows and m columns. So, we say this is an n by m matrix. Okay. So, this has n rows and m columns. Okay. And this notation is very useful where we just denote the various elements. Okay. So, A I j is the element belonging to the ith row and jth column. Okay. So, we will be following this notation throughout. We will use capital letters to denote matrices and small letters with the subscripts to denote the appropriate elements of matrices. Needless to say, for a square matrix, has m equal to n. So, number of rows equal to number of columns. Okay. So, for a square matrix, so you typically have you denote it by A n n. Okay. So, it is an n by n square matrix. Okay. So, this is the basic of matrix. Now, you can ask where is this useful and what are the properties of matrices. So, let us look at some basic properties of matrices. So, I will just go through this very quickly because I am sure many of you are familiar with these. So, as far as addition and multiplication goes, okay. So, A, which is a matrix, and B, which is also a matrix, okay, can be added only if they have same number of rows and columns. So, if you want to add two matrices, they should have the same dimensions, they should have the same number of rows and same number of columns. So, if you had A plus B, if it was C, then I can write that Aij plus Bij equal to Cij. This is the rule for matrix addition. So what this means is that you have to add the elements term by term. That means you have to add the ijth element of A to the ijth element of B to get the ijth element of C. Okay. So if A is an m by n matrix, and B should also be an m by n A matrix, and C also is an m by n matrix. Okay. What about multiplication? So in multiplication, you can multiply an m by k matrix with a k by n matrix to get an m by n matrix. So what I want to say is that you can multiply two matrices only if the number of columns of the first matrix is equal to the number of rows of the second matrix. And the rule for matrix multiplication is that, suppose I want to calculate Cij, the ijth element of C, then what I have to do is to sum over some other index. I will just call it L, A I L, B L J. Okay. So I sum over all L, okay, and L should go from 1 to k. Okay. So again I am not doing this in all detail because I am sure many of you are familiar. So if you have a matrix that looks like this, okay, and you have another matrix that looks like this, where the number of rows here is equal to the number of columns here, okay, then when you multiply these, you will get a matrix that has this many rows and this many columns, right. So you will get a matrix that has this many rows and this many columns. Okay. So so if this is m and this is k and this is n, then this is m and this is n. Okay, m by n matrix. Okay, and the way you get it is you take the elements of the row and you multiply them by the elements of the column. Suppose I want to find the first element of this matrix. Okay, then I have to take the element of the first row and the first column of n and multiply first. First I multiply these two, then I multiply these two, then I multiply these two, and I go on and on. Then I multiply these two, and then I go on and on till I reach the end. Okay. So you have to multiply them term by term. So this element multiplies this element multiplies this element multiplies this element, and so on all the way up to the end. And when you do that, when you add all of them up, you will get this particular element. So that's so much for addition and multiplication of matrices. There are a couple of other operations that you can do. One is called a transpose of a matrix. Okay. So we will again we will restrict the discussion to square matrices. See, so that is m equal to n. So suppose you have a matrix A, okay, which is a square matrix A, okay, and A transpose is so if this is A11, A12 up to A1n, A21, A22 up to A2n, AN1, AN2 up to ANN. Okay. Then if this is A transpose is given by the matrix where the rows and columns are swapped. So what you have is A11, A12 up to A1n, A21, A22 up to A2n, AN1, AN2 up to ANN. Okay. So that is A transpose. So I can write Aij is your element of A, then the corresponding element of A transpose is Aj. So Aij and Ji are swapped in A and A transpose. So when you go from A to A transpose, you are swapping the off diagonal elements. So, diagonal elements are not affected because AII remains the same. Okay. The next thing is called the trace. So, trace of a matrix again we will restrict to square matrix. So, trace equal to sum of diagonal elements. Okay. So, trace of A is equal to sum over I equal to 1 to n A I. Okay. So, this trace sometimes plays a role in various operations. So, these are some basic matrix operations. There are some other useful operations or objects that are defined in relation to matrix, and this is a determinant. So, suppose you have again only for square matrices, determinants are only defined for square matrices. So, if you have a matrix A which is an n by n matrix, okay, then you can write determinant of A, okay, you can write it as in the following way. So, what you will do is you will write it as A11 times, write this as what is called a cofactor of A11 plus A12 times cofactor of A12 plus dot 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 up to A1n times cofactor of A1n. Okay. I will just explain what this is. Okay. To motivate the determinant, okay, we can so I can write this in general as A sum over I A1I times cofactor of A1I. So, I will come to what the cofactor is, but for just to initiate the discussion, suppose you have a 3 by 3 matrix. Suppose you have A 3 by 3. Okay. So, this is denoted by A11, A12, A13, A21, A22, A23, A31, A32, A33. Okay. So, this is my matrix A. Okay. Then determinant of A is denoted by the same matrix with straight lines. So, instead of these square brackets, you have straight lines. Okay. A12, A13, A21, A22, A23, A31, A32, A33, and this is equal to, I'll write it in 3 lines here. So, it is A11 times A22 into A33 minus A23 into A32 plus A12 into A23 into A31 minus A21 into A33 plus A13 into A21 A32 minus A31 A22. Okay. So, it is a sum of 3 terms, okay, just as you can see from this expression that it is a sum of 3 terms. Okay. Now, how did we calculate the determinant? We multiplied this A11 by what is called the cofactor, which is nothing but this determinant. Okay. Then we multiplied A22, which I will show you with a different color, with this. So, you remove this row and this column. So if I imagine that I take out this row and this column, okay, then I get this determinant which starts with A23, A33, A21, A31, and so I just have the value of that determinant is A23 times A31 minus A21 times A33. Similarly, for A31, what I do is I remove this row and this column, okay, and I multiply it by this factor. So that is the basic idea of a determinant, okay, that you write it in terms of these cofactors. So just to remind, so cofactor of A11 is equal to A22 times A33 minus A32 times A23. Okay. This is nothing but determinant of the matrix formed by removing this row and this column. So, A22, A23, A32, A33. Okay. So, this is the basic idea, and you can do this for larger matrices also, but you will have to calculate more and more determinants. Okay. So, this cofactor is nothing but a determinant of a smaller matrix. Cofactor is the determinant of the matrix with one row and one column removed. So, now that we have the idea of determinants, we can go ahead to the next operation. I'll also mention one more thing, that if you look at any term in the determinant, okay, it will have a product of three of the elements of the matrix. So, for example, this term A11 times A22 times A23 is a product of A11 times A22 times A33. The next term, which is A11 times A23 times A32, is a product of this times this times this. So, each term in the determinant contains exactly one element from each row and each column. Okay. So, there is exactly one element from each row and each column. You can never have a product that involves two elements from the same row or two elements from the same column. Okay. Every product has one element from each row and one element from each column. I will just make a note of this. Each term in determinant has a product involving exactly one element from each row and each column. And this is again a very important fact to note, that you never have two elements from the same row multiplied in a determinant, okay, in a determinant expression. Okay. The next operation for matrices, okay, so this has to do with inverse, and in order to define the inverse, again this is only for square matrices. Okay. So, in order to define the inverse, we define something called an identity matrix I. Okay. If you have an n by n matrix, okay, so this is the diagonal elements are 1 and all the off diagonal elements are 0. So, all the off diagonal elements are 0, all the diagonal elements are 1. Okay. So, that is what is called an identity matrix. Okay. And identity matrix has the property that any matrix multiplied by the identity matrix, okay, gives you A, gives you the same matrix. That means, and again let us restrict to square matrices. So, let us take an n by n matrix and you take an n by n matrix, okay, you get A, just n by n. So, an identity matrix is like the unit in multiplication, it is like 1. So, any scalar multiplied by 1 gives you the same scalar. So, any matrix multiplied by identity gives you the same matrix. So, it is like your 1. Okay. And so now you can ask suppose A times B equal to identity, okay, then B is called inverse of A, and we can write B equal to A inverse. Okay. So, in other words, A times A inverse is equal to identity, which is also equal to A inverse times A. Okay, again it is not hard to show this, okay, but basically A times A inverse is identity, and so now we have defined the inverse of a matrix. This is inverse of matrix A. Okay, so inverse of a square matrix is also a square matrix, okay, and again the matrix inverses are something that we end up using a lot. Matrix operation that I want to talk about is that of row and column operations. Okay, so suppose you have a matrix A. I'll just take a simple matrix A denoted by A11, A12, our usual matrix. It should be A1n, A21, A22, A2n, AN1, AN2, ANN, and I can do this for square or rectangular matrices. Okay. Now a row matrix, so a row operation is something like, so suppose you take R2 plus C times R1. Okay, so what you mean by this is row 2 plus C times row 1, okay, and you call this as row 2 is equal to row 2 plus C times row 1. So what you mean, you will get a new matrix, okay. What does that new matrix looks like? It looks like the first row is unchanged. To the second row you add C times the first row, and you have to do it element by element. So what you do is this element becomes A21 plus C A11. Okay. Similarly, this element becomes A22 plus C A12, and the last element becomes A2n plus C A1n. Okay. And all the other elements remain unchanged. Okay. So only row 2 is changed by this operation. This is called a row operation. You can multiply any constant, you can subtract, and you can add two different rows and so on. So this is called a row operation, where you add one row to another, or you take linear combination of rows. You can also have column operations. So column operations can be similarly defined. Operations can be similarly defined. Okay. So for example, if you have the same matrix A, okay, and so you have the same matrix A, which is an n by n matrix, and you do a column operation where let us say you do C2 equal to C2 plus D times C1. Okay. So what does that mean? That means you don't do anything to column 1, A11, A21 up to AN1, but to column 2 you add D times column 1. So what you will get is A12 plus D A11, A22 plus D A21, and all the way up to AN2 plus D AN1. Okay, and then all the other elements are all the other columns are unchanged. Okay. So what you did by this is, by these row and column operations, you get new matrices, and there are some interesting properties of these row and column operations. One of the things is that when you do these row and column operations, the determinant is unchanged. So row and column operations leave determinant unchanged. Okay, you can show that row and column operations leave the determinant unchanged. Okay, we'll discuss some properties of determinants a little later. Okay, but we'll just keep in mind right now that when you do row and column operations, then the determinant of the matrix is not changed. Okay, thank you.